Welcome back. In the previous lecture, we learned that the unitary transformation on a qubit is simply a rotation of its Bloch vector. In this lecture, we realize a rotation by a large angle as a sequence of many rotations by a small angle. So, just to summarize what we have done so far, we are talking about qubits, and so the statistical operator for a qubit, the state operator, is characterized by this Bloch vector S, which is a vector which does not exceed 1 in length. And if we have transformation on this row by a unitary operator where the U transforms the kets and the U adjoint transforms the bras, and so each ket bra that is contributing to rho is transformed by a U adjoint combination in this sort of sandwich structure. Then the rho is transformed into a new rho where the S turns into S prime, and the S prime is just the original S rotated around the direction of E. This is a unit vector by the angle 2 phi. So it's cosine phi and sine phi here, but the rotation is by the angle 2 phi. Now, it should be clear that if we have one such U that describes a rotation around E by an angle phi, say we are rotating by an angle phi 1, and then we are rotating a second time by angle phi 2, but it's the same rotation on direction E, the same axis of rotation specified by the unit vector E. Well, then this is just rotating by the angle of phi 1 plus phi 2. So I'm rotating by some angle, I'm rotating by another angle. That's like one rotation by the sum of the angles. And it doesn't matter clearly in which order this rotation is done. So we can also first act with rho of phi 2 on the kets, and then with rho of phi 1, and the overall transformation will just be a rotation that goes with the angle of phi 1 plus phi 2. Now this is reasonably obvious, but we can also show it by just making use of this particular structure of U and multiplying one U with phi 1 by the other U with phi 2, and then arriving at an expression like this. But we leave this to the audience as an exercise. Let's look at a particular situation where we rotate around the y-axis by angle 2 phi equals 180 degrees. So if the Bloch vector is in the z direction upwards to begin with, and I rotate in the xz plane by an angle of 180 degrees, then I end up with the Bloch vector pointing in the negative z direction. And now, pointing up in the z direction, pointing down in the z direction, these are orthogonal states of the qubit. So let's just be more specific. So we have a rho which is initially just a projector on the z operator equals +1, and then this rotation turns this into 1 minus z. So if I probe the system by a z measurement, and then I would have the +1 outcome directed here, and the -1 outcome goes here to a detector. Then with this initial state, I will just have 100% of the systems being detected here, and none at all detected at this outcome. However, having checked this, and now I'm progressing, and now I'm implementing this rotation by 180 degrees around the y-axis, then after that, rather than have rho equals 1 plus z half, I have 1 minus z half. And if I now probe in the z direction, then I no longer find the value +1, I only find the value -1, because what was pointing up before is pointing down now, and so it goes to the -1 exit in a Z measurement, 0% here. Well, what if I break up this rotation by 180 degrees into, say, two rotations by 90 degrees? If I have the phi1 plus phi2 equal 180 degrees, and the phi2 and the phi1 individually 90 degrees. Well, that's just two of these rotators followed one after the other, but the overall effect is still the same, because rotating by 90 degrees and then rotating by another 90 degrees is just the same as rotating by 180 degrees. I can also rotate by 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees, 30 degrees 6 times, and still get 180 degrees. A new situation arises if, after each of those rotations, we check whether we still have the original state. So just to be more specific, if I begin with a row which is half of 1 plus z, and then I do this rotation by an angle 2 phi, so I'm making use of a u like this, then after that I have the row prime, which is half of, and now I have rotated around the y-axis, so it's cosine 2 phi times z plus sine 2 phi times x, because turning the x around the y-axis turns it into a combination of z and x, depending on the angle of rotation. And if this is now fed into a z measurement device, then I have the outcomes with probability -1 and +1. And what are the probabilities for that? Well, the probability here for +1, that probability is the trace of the row in question, which is the row prime, and the probability operator for this outcome of the measurement, which is the projector on z being +1. And so we work this out and we find a half of 1 plus the cosine of 2 phi, the coefficient of z here, and that's the cosine of phi squared. So this probability is the cosine of phi squared. And then the probability for getting the outcome -1, that will be half of 1 minus the cosine of 2 phi, the sine of phi squared. And of course, the two probabilities add up to 1, so the probability for this result is sine of phi squared. So now let's see what happens if the rotation by 180 degrees is done in 3 steps of 60 degrees each. So we begin with the original row, which is the half of 1 plus z, and we feed this into a first rotator where the 2 phi is 60 degrees. And then we monitor whether we still have z, so we make a z measurement. And if we find the +1 outcome, we continue with another rotation by 60 degrees, followed by another checking of what is the situation. And if we find +1, we continue with the third rotation by 60 degrees. So in total, we have 60 degrees at 60 degrees, 180 degrees, followed by a final checking of what is the value of z, and we again select +1 outcome. So without this monitoring in between, the total rotation is just 100 degrees, and we know that the probability for finding +1 at the final stage is just 0. But now the probability of making it from here to here is the cosine of 30 degrees squared. And then we have another probability of a cosine of 30 degrees squared, and final probability of cosine of 30 degrees squared. So the total probability is equal to the cosine of 30 degrees to the sixth power. Now the cosine of 30 degrees is half of the square root of 3. You take this to the sixth power, you get 27 divided by 64, which is about 42%. So without the monitoring in between, we have 0%. With the monitoring in between, 42% of the systems that are fed in, all prepared with the Bloch vector pointing in the z direction, having unit length. Here we're checking, are we still having the same situation as before? Do we still have the Bloch vector pointing in the z direction with unit length? And if the answer is yes, then we continue, rotate. We ask again. If the answer is yes, we continue to rotate. Finally, we ask again. And so the original state survives this multi-step procedure with a probability of 42%. If we would not do the monitoring at the intermediate stages, we would just take this thing, rotate by 60 plus 60 plus 60 by 180 degrees, and the probability would be exactly 0. Now, if we break it up into more pieces like this, so we have the individual probability, the cosine of phi squared, and then we do this n times for the phi equal 180 degrees by 2 times n, 2 because of this factor of 2 that's appearing in this rotation, and divided by 2n, then we take this to the n powers. And then if the n is very large, then this is approximately 1. So these individual probabilities will all be very large because the individual angles are very small. So we have very many rotations by small angles, such that in total there are n of these rotations, and with n of these rotations we get a 2 phi, which is equal to 180 degrees. But if after each of the rotations we monitor the system, then nothing really happens. We begin with this state, and with a probability of close to 100%, which is this getting close to 1, with a probability close to 100%, we still have the initial state. So what we see here is a phenomenon which is known as the so-called quantum Zeno effect. Which makes reference to a Greek philosopher that lived some 2,000 years ago, long before people knew anything about quantum physics. But anyway, there's an allusion to this Greek philosopher. The point is, and the important point for us is that if there is a quantum system that is monitored, then the quantum system evolves in a way that can be very, very different from the quantum system that is not monitored. So let me just repeat. We started with 60 degrees, 60 degrees, 60 degrees. We rotate about 180 degrees, but we do that in 3 steps. And after 3 steps, we check, well, is the system still in the state that it began with? And the probability after the first step is just a probability of cosine of 30 degrees, which isn't very large, but it's not 0. And then we do this again, and we do this again, and we do this again. And in every step, we have a probability of 30 degrees. So we have implemented a rotation of a total of 180 degrees in steps of 3 times 60 degrees. So if this monitoring, the watching of the system would have no effect, then the probability at the end would be 0. But the watching of the quantum system has an effect. It is different from watching a classical system. If a car drives by and you watch it, it has no effect on the car. But if you have this quantum system undergoing an evolution and you watch the system as it undergoes the evolution, that has a very strong effect, or at least can have a very strong effect, on the evolution of the system as it progresses. In summary, we can compose many rotations by a small angle and so realize a rotation by a large angle. When we monitor the system by intermediate measurements, the quantum Zeno effect prevents the quantum system from evolving. In the next lecture, we consider quantum states of qubit pairs, which we build from single qubit ingredients.